This is the second Chemistry Chapter 8 lecture. You'll need to have your notes out. We're at the top of page 4. And have your periodic table handy. And so that you can see it better, I went ahead and took a Sharpie and marked the columns from S block and P block. So 1, 2, 3, 4, 5, 6, 7, 8. I'm not sure you could see it all that well on the last lecture. So I'm going to draw you, we're going into, whereas the last lecture we talked about ionic compounds, we're going to talk about the Lewis structures of covalent compounds. And instead of taking and giving electrons, in this lecture we're going to be sharing electrons. All right, so let's start with F2. All right, so fluorine is in column 7, so it has 7 valence electrons. Okay, so let's draw. So we would have a Lewis structure, and there's 2 of them. All right, so with covalent compounds, what happens is that each fluorine wants to have 8 valence electrons, right? The octet rule that we talked about in the last lecture. So one way for each fluorine to get 8 valence electrons would be if they could share this unpaired electron. All right, the paired electrons really don't interact, okay? They are in a stable space. However, these unpaired electrons aren't stable and they're able to interact. So we could draw it, if I drew one on top of the other, we could draw it something like this. And here you would have a shared electron pair. All right, so this shared electron pair is called a covalent bond. All right, so the way that we show those covalent bonds, though, is with a line and not dots. So I'll show you how to do that in just a second. So if we go back to your notes, all right, covalent bond is a shared pair of valence electrons that holds atoms together in covalent compounds. Covalent compounds share electrons and are called molecules, whereas ionic compounds give and take electrons and are called ions. So shared electron pairs in Lewis structures are represented by a line. So let's draw this fluorine again, and instead of the double dot that's shared, I'm going to draw one on top of the other. You could draw them side by side also. That shared electron pair we represent by a line, and then all the other pairs are by dots. So each line counts as 2 electrons. Okay, so remember, octet rule, want to have 8 electrons in the outer shell, so we'd have 2, 4, 6, and the line counts as 2, so that's 8. And for this fluorine, 2, 4, 6, and it gets to count the 2 of that line also, so it has 8. All right, so moving on down your notes, before I erase that, general guidelines for determining the Lewis structures of a molecule. You want to draw the Lewis structure of each atom. You'll get to the point where you don't have to do that. But in my first example, we're going to do that. Put the atoms with the most unpaired electrons in the center, okay? The atoms that have the most single dots, unpaired electrons. And then try to arrange so that all the atoms have 8 electrons, except for hydrogen. Hydrogen only wants to have 2 in its outer shell. Okay, but all the others, since these are covalent compounds, there won't be any metals. Everything is striving for the octet rule except hydrogen. All right, in your book, open to 268. And let's do on your own 8.10. Okay, the first one that we're going to draw is NH3. All right, covalent compound, no metals. So the Lewis structure for hydrogen would just be one electron. All right, hydrogen's in column 1 on the periodic table, just one electron in its outer shell. But there are 3 hydrogens, so I drew all 3. I won't always do this, just on this first time. Nitrogen is in column 5, so it has 5 valence electrons. And so I'm going to draw it out here. So if you went around the horn, it'd end up looking like this. So you would have 1 pair that doesn't interact and 3 unpaired electrons. So what's going to happen is each of those unpaired electrons will form a bond with hydrogen. That makes each hydrogen happy, and it gives nitrogen the 8 electrons that it wants. So let's put nitrogen in the center. We would have hydrogen with 3 single bonds, and then don't forget that electron pair that's right here. So this is the Lewis structure for hydrogen. Let's count. Each hydrogen wants 2, for NH3. So 2, 4, 6, 8 for nitrogen, and then each hydrogen has 2. So that would be the correct Lewis structure for NH3. All right, I'm going to erase each time, but you'll have to squeeze this into your area on your notes. All right, SiBr4. So silicon is in column 4. It has 4 valence electrons, so I'm going to draw its Lewis structure. And then each bromine is in bromine's in column 7, so it has 7 valence electrons. Now I'm not going to draw all 4 of them, but all 4 of them would have this same situation. So each bromine has 1 open slot, so it just wants to form a single bond with one of those unpaired electrons with silicon. So if I were to draw 3 more bromines, you would have it happen 3 more times, those single bonds. So the most unpaired electrons would be silicon. That goes in the center, and it would form a single bond with each bromine. Now don't forget to draw all the electron pairs around bromine. See, still those 2, 4, 6, those didn't go away. Now let's count and make sure that we have 8 electrons around each atom. So silicon, 2, 4, 6, 8. Bromine, 2, 4, 6, 8. And that's true for all of the bromines. So this would be the correct Lewis structure for SiBr4. All right, the next one is H2S. All right, each hydrogen, I'm not going to draw both, but each hydrogen has 1. And then sulfur is in column 6. So it has 6 valence electrons. So each of those unpaired electrons on sulfur could form a single bond with each hydrogen. If I were to draw another one, it would do that. That would make hydrogen happy because it gets to count sulfur's unpaired electrons, so it has 2. And then sulfur would have 2, 4, 6, 8. So put sulfur in the middle because it has 2 unpaired electrons. And then we'll do a hydrogen. And it doesn't matter if you wanted to draw that hydrogen going south or that hydrogen going north, that would be fine. But don't forget, I drew them on each end like this. But where you draw them matters much more in Chapter 9 than Chapter 8. So we still have to draw these two electron pairs. Each hydrogen has two, and then sulfur has 2, 4, 6, 8. All right, in part D, ICL. Okay, iodine, look at it, it's in column 7, so 1, 2, 3, 4, 5, 6, 7. Chlorine also, look at your periodic table in column 7. So each of these atoms would be happy with just one more electron, then they'd have 8. So we could just form a single bond between the two unpaired electrons. Since there's just two, there's no central atom here. So just a single bond. And both iodine and chlorine now have the octet rule completed, and each has 8 electrons. All right, so let's move on to the next page in your notes. And this section is called More Complicated Lewis Structures. So we're going to talk about a double bond and a triple bond. Now the most famous double bond is with oxygen. So let's say we have O2. So oxygen, each of these two oxygens, if we were to draw the electron dot diagram, all right, we would have, we did one on top of the other here. Okay, so each oxygen needs 2 more electrons. So we could have this one maybe pairing with that one, and this one could pair or share that one. And what happens in this situation is you'd have what's called a double bond. So we would show that with 2 lines. We still have to draw the 2 electron pairs around each oxygen, but 2, 4, 6, 8, 2, 4, 6, 8. So remember, each line counts as 2 electrons. Okay, let's talk about a triple bond. The most famous triple bond is nitrogen. So each nitrogen would have, it's in column 5, right? Oxygen was in column 6, nitrogen column 5. So 5 valence electrons. So we would have something like a share there. Could have a share there. Wow. And a share there. So that would make a triple bond. But don't forget about that electron pair, that each nitrogen has an electron pair that you have to continue to show on each one. So 2, 4, 6, 8, 2, 4, 6, 8. All right, let's do a couple of example problems from the book. So if you'll flip over to page 272, we'll do 8.11 and 8.12. All right, 8.11 says draw the Lewis structure for CH2O. Okay, let's draw each one here. Carbon's in column 4, so 4 valence electrons. Each hydrogen in column 1, and oxygen is in column 6. All right, so carbon needs to share, it needs to form a bond with each one of these single electrons, okay? So it could form a bond with each hydrogen, okay? So we're going to put carbon in the center because it has 4 unpaired electrons. It has the most. So let's draw a hydrogen and a second hydrogen. Now, those 2 hydrogens are happy. They both have 2. what kind of bond between carbon and oxygen? Well, oxygen has 2 empty slots. There's only 1 oxygen, so we could form a double bond. If there were 2 oxygens, we would have a single bond with each one. But in this case, there's just 1 oxygen, so it would form a double bond, a stronger bond. So the carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Each hydrogen has 2. It doesn't matter if you put the oxygen going north or each hydrogen, something like this. I don't really care so much as long as you have the bonds shown. We don't really care so much about the shape here in chapter 8. All right, let's do one more. This is 8.12. And it says C2H2. So carbon's in column 4, and we have 2 of them. And then we have 2 hydrogens. All right, so we've got 2 carbons. The only way to make this work is to have each hydrogen form a bond with one of the carbons, but not both hydrogen on one carbon. I'll show you how that wouldn't work in a minute. Okay, so we know the 2 carbons would have to go in the center because they have the most unpaired electrons. So I'll draw it like that, the 2 hydrogens. Now what kind of bond would work? Well, there's 3 unpaired electrons on each carbon, so we would have a triple bond. So now each hydrogen has 2, and each carbon has 2, 4, 6, 8. All right? Now let's say, so this is the answer. This is what works. Let's say you decided you put the 2 carbons in the center, but you wanted to put both hydrogens on one carbon. Then all that's left for this carbon would be a double bond, right? But then this carbon over here is not happy. It only has 4 valence electrons. It wants 8. Okay, so that's why this would not work. And you have to monkey with it until you can get either 2 around hydrogen and 8 around everything else. All right, so we're almost done with this chapter. Let's look at the very bottom of your notes. And we are on page 219. And here are some applications of Lewis structures. These Lewis structures are what helps protect us from some of the sun's harmful energy. Okay, so we talked about that in chapter 7. The most powerful energy that comes from the sun would be gamma rays. All right, gamma rays would go right through our skin and damage our organs. So we need to be protected from those. What protects us from gamma rays would be the triple bond that we drew just a minute ago of nitrogen. Those gamma rays, when they hit the triple bond of nitrogen, they break that bond. But then all their energy goes into breaking that bond, and the gamma rays are rendered ineffective. Okay, all their energy is lost breaking the bonds of nitrogen. And this nitrogen, the atmosphere, right, is 78% nitrogen. Okay, so we have a lot of protective nitrogen up in the atmosphere to block the gamma rays. Second would be X-rays. So X-rays, you go to the dentist, you get an X-ray, you know that they will penetrate the skin and bounce off your teeth, or if you've broken a bone, they will bounce off your bone and render an image on the camera. So definitely powerful rays that could do damage to you. Those are blocked by what we've already drawn, the double bond of oxygen. So those X-rays, when they hit that double bond, they bounce off the triple bond of nitrogen. So they don't lose any energy there, they just bounce off. But they break the double bond of oxygen. And then all their energy is dissipated by that double bond, all right? So we know that that, you know, oxygen, I believe, is around 21% of the atmosphere. So there's plenty of oxygen to take care of X-rays. And then we have UV rays. UV rays, you've experienced that if you've ever gotten a sunburn, all right? So not as powerful as X-rays or gamma rays, but definitely can do some damage. And we are protected by a molecule called O3. The name of O3 is ozone. Maybe you've heard of the ozone layer before, and maybe you've heard of how certain parts of the Earth have had a hole in the ozone layer. And we've had to make some environmental laws to try to protect the ozone layer in the atmosphere. Well, ozone looks like this. It has O3, it has a double bond and a single bond with oxygen. Okay, so UV rays aren't powerful enough to break the double bond, but they do break the single bond in ozone. And then when they break that bond, all their energy is dissipated. So if we didn't have the ozone layer, we would really have to protect ourselves a lot more from UV rays. We would always have damaged skin from that. So that completes Chapter 8. Let's talk about the homework from Chapter 8. Okay, so the homework before, really your homework is just to finish up. So we have the review questions on page 283. You can finish those up by doing 9 and 10. And the practice problems from page 284, right? You want to finish those up by drawing, I don't think all of them are drawing, but 7, 8, and 9 appear to be. So do 7 through 10. If you are having any trouble with this, so you've watched my lecture here and you're still just having trouble getting it, what I want to suggest is that you read the blue example problems. This is going to be true for the entire book. Read the blue example problems. Read example 8.4. The author does a great job of explaining. Just read through those, okay? And there's another one to read. You could read 8.5 on page 271. Read through that. He takes a very careful explanation and also one that has carbon and nitrogen in it on the next page, 272. So read through those blue example problems if you're having trouble. It's worth your time. And I will talk to you next video.